This wild and majestic jaguar is on the hunt for the mole. Hi everyone, today we're going to be going over the 50s, which is empirical and molecular formulas. On the test, these are the parts that we would have on the test and the page numbers that would go with them. When we're talking about empirical molecular formulas, those are the easiest formulas, the formulas in lowest terms, and molecular formulas are the true formulas. We'll get to more of that as we're going along. Here's a little joke for you. He said, "You were smart to come and see me, Mr. Lewis. These moles on your back definitely look suspicious." So we're going to go over the front page, 50.0. It says formulas like NO2, nitrogen dioxide, show that there are twice as many oxygen atoms as there are nitrogen atoms. In other words, there's a 2-to-1 ratio. 2 oxygens for every 1 nitrogen. Formulas like H2O show that there are half as many oxygens as hydrogen atoms, or there's twice as many H's for there are number of O's. So there's twice as many hydrogens as there are oxygens. In 1 mole of water, there's 2 moles of H and 1 mole of O. So 1 mole H2O has 1 mole of oxygen, and it's got 2 moles of hydrogen. That is if we had 1 mole of water. Subscripts indicate atom ratios in a molecule. So in 1 molecule of MgCl2, there's 1 atom of Mg and 2 atoms of Cl. Subscripts indicate mole ratios in a compound. So if we have 1 mole of MgCl2, we would have 1 mole of magnesium and 2 moles of Cl. So now we're going to play around with empirical molecular formulas. So in the formula N blank O blank, the blanks could have many numbers in them. The following 8 compounds are known to exist with just nitrogen and oxygen. So here are the compounds with nitrogen and oxygen. The formulas above are called molecular formulas because they are the proper formulas for these molecules. If a formula is divisible by some whole number, it is then called an empirical formula. So if we look here, molecular formulas are the actual formulas or the true formula. What is the actual compound? That is the molecular formula. The empirical formula is the simplest formula, the lowest terms formula, or like I like to call it, the easy formula, because the 2 E's kind of relate to each other. So if we look here at this molecular formula, there's no way of reducing it. So the empirical molecular formula are exactly the same. Same thing with this next one. You cannot reduce NO2 to anything. So the empirical and the molecular formula are exactly the same. Same thing with nitrogen trioxide. Same thing with dinitrogen monoxide. But now we get to these last 4. Can I reduce this one? Can I reduce this N2O2, this dinitrogen dioxide? And the answer is yes. I can reduce it to NO. That is the simplest formula for this molecular formula. So this is the empirical formula. This is a molecular formula, and sometimes the empirical and molecular formulas are exactly the same. Can I reduce this one? I cannot. Can I reduce this one? Yes, I can. I can reduce that to NO2. And can I reduce this one? The answer is no, I cannot. So if we look here, this is the work that we just did. Only 2 of the last 4 molecular formulas could be reduced. The empirical formula of N2O2 is NO. The empirical formula of N2O4 is NO2. Again, empirical, the easiest, simplest, or lowest, or reduced form of the molecular formula. If we look here, These two have the same empirical formula, but chemically they are different from each other because they have a different molecular formula. So these two chemicals would react differently, but their empirical formulas are exactly the same. Figure out the empirical formulas of these compounds. So pause the video and reduce each of these compounds. So that's that one reduced. You could divide each by 6. This one you divide by 2. And this one you divide by 2 as well. And that's where you get your answers. So empirical formulas are the reduced formulas, the easiest formula. And these are the molecular formulas, the true formulas of those chemicals. This machine, when you go off to college, might look a little different. This is a mass spectrometer. When I went to college, they allowed us as freshmen to inject chemicals into this machine, and it would spit out a bunch of percentages. And from that, you could figure out what chemical compound you actually had. This machine at the time that I used it was hundreds of thousands of dollars. They may have become a little bit cheaper, but when you go to college, they'll still let you guys use this. You might see this on a lot of the CSI shows, the crime scene investigation type shows. They'll take a syringe, they'll shoot it into this machine right over in here. It'll run it all the way through the machine, and it'll spit out some percentages for the chemist to analyze. So on a CSI show, they might have a white powder. They might want to find out if it's cocaine or heroin or baby powder or rat poison. They would inject it into this machine. It's going to spit out some percentages. And from that, the scientist can figure out what the actual compound is. This is on the cover of your unit pack, and it's also on the top of your 50s as we're working along. I'm not going to read through all this right now, but I'm going to as we go through the next problem. So this is the first problem. It's done for you at this point in time. I'm going to go through the steps, though. So it says the molar mass of nicotine, one of the most addictive drugs in the world, is 162.15 grams per mole. So if I have 1 mole of it, it's going to have a mass of 162.15 grams. Nicotine was analyzed using the mass spectrometer and found to be 74% carbon, 8.65% hydrogen, and 17.35% nitrogen. Find the empirical formula and its molar mass, show your work, and then find the molecular formula. So I'm using the cover of your unit pack, or you could be using the top of this page. It doesn't matter. 1, it says, if given percentages, assume a 100-gram sample. So the percentages are grams. So I don't look at this and say it's 74% carbon. I say it's 74.00 grams of carbon. And I write that down right here. I do the exact same thing with the hydrogen. Those percentages turn into grams. And you're going to want to write this to the far left and as high up as you can in the blanks that you have to work. And 17.35% nitrogen is 17.35 grams of nitrogen. That's step 1. Step 2, convert the grams to moles for each element. So we've done these problems. We go have grams of carbon here. So we put grams of carbon here. We go to moles of carbon right here. We use the molar mass, and we get an answer with the correct number of significant digits. We do that for the hydrogen, and we do that for the nitrogen. If we look at the hydrogen, we have 3 sig figs here, 3 sig figs here, infinite sig figs here. So we can only have 3 sig figs in that problem. This one has 4. This one has 4. Infinite. 4, 4, infinite. So that's why this one has 4 sig figs and this one has 4 sig figs. So I'm going to erase all that, but that would be your first step. That's steps 1 and 2 on your chart. Now it says for 3, find the ratio between elements by dividing by the smallest number of moles. So I'm going to take this carbon, I'm going to put C right here, and I'm going to put this number as a subscript on that carbon. I'm going to take this hydrogen that we have right here, and I'm going to put this number as a subscript on that hydrogen. That's right there. And I'm going to do the exact same thing with the nitrogen. Nitrogen's right there. I'm going to put that with a subscript. So that's what I have right up here. It's all typed in for you. So I put those as subscripts. And I look at those 3 numbers, and I decide which of these 3 numbers is the smallest. This is the smallest one. I divide that through each of them. And now I get a mole ratio. The reason we have to do that is we can't have 6.162 atoms of carbon. You either have to have 6 atoms or 7 atoms. You couldn't have a fraction of an atom. Same thing with the hydrogen, same thing with the nitrogen. So that's why we're doing this step, is to try to get to whole number atoms in a molecule. I do this math following the sig fig rules, and I get C 4.977, I get H 6.99, and I get nitrogen 1.00. It says for number 4, it says make sure the mole numbers are whole numbers. If the tens place is a 9, you round up. If the tens place is a 0.1, if the tens place is a 1, you round off. So this C, this tens place is a 9, so I can round this to a 5. In the hydrogen, this tens place is a 9, I can round this to 7. And in nitrogen, I can round that to 1. So I have 5 carbons, 7 hydrogens, and 1 nitrogen. And this is my empirical formula, the simplest formula I can have. I then am going to find the mass of my empirical formula. So right here, I find the mass of my empirical formula. Do you have to show your work? Not really, but that is the work that would go along with it. So I find out that my empirical formula has a molar mass of 81.06 grams per mole. So I know the empirical formula mass. I was given the molecular formula mass in the problem. So I take the molecular formula mass, I divide it by the empirical formula mass, and I should get a whole number. I multiply that whole number through my empirical formula, and I get C10, H14, N2. So that is what I am all given. So my empirical formula, I wrote it down. I found out the molar mass of it. The molecular mass is twice as heavy as the empirical mass formula. So therefore, I'd multiply 2 through the empirical formula and get the molar mass. Now I'd have to go through some kind of catalog, some kind of book, or type it into the internet to find out what that chemical actually is. So now we're going to go through this whole problem without it being all typed up for us and following the steps. So ascorbic acid, vitamin C, contains 40.92% carbon, 4.58% hydrogen, and 54.50% oxygen. What is the empirical formula and molecular formula for ascorbic acid? Ascorbic acid has a molar mass of 88.03 grams per mole. So step 1, right off the cover, if given percentages, assume you have a 100-gram sample. A mass spectrometer is always going to give you percentages. So I don't have this percent, I have that many grams of carbon. So I go 40.92 grams of carbon. And I'm going to go to step 2 right away with this one. I'm going to convert it to moles. So grams of carbon, moles of carbon. And I have to go to the molar mass. Anytime I go between gram island and mole island, I find the molar mass. The molar mass is 12.01 grams in 1 mole. I solve that, and I end up getting 3.407 moles of carbon. And that's with correct sig figs. This should all be in the upper left-hand part of this problem, trying to write as neat and as small as you possibly can. Then I do it with the next one, 4.58% hydrogen. So 5.48% hydrogen, grams of hydrogen. Grams of hydrogen. And I convert that to moles. 1.00 grams of hydrogen, 1 mole of hydrogen. And I solve that, and I get 4.58 moles of hydrogen. why don't you pause the video and do the next one yourself and see if you're getting this. Why don't you see as far as you can possibly get into this problem, and if you get stumped, then play that part of the video. I'm given 54.50% oxygen, so 54.50 grams of oxygen. Grams of oxygen go on the bottom. Moles of oxygen go on top. That's 16.00 grams in 1 mole. And I solve that, and I get 3.406 moles of oxygen. Now I'm going to erase all this because I need some room. You need to keep that on your paper. But that's what I have right now. Step 2 says make mole ratios. So I take this carbon and I give it a subscript that I just calculated, 3.407. Take the hydrogen and I give it its subscript, 4.58. And I take the oxygen and I give it its subscript, 3.406. Okay? So this is number 3. I'm going to erase this, get it out of my way. Now I look at those 3 numbers and I divide by the smallest one. And the smallest one is this one right here. So I divide it by 3.406, 3.406, 3.406, and I get carbon at 1.000. I get hydrogen at 1.34 with correct sig figs, and I get oxygen at 1.000. Now, the whole point of doing this step is you can't have 3.407 atoms of carbon in a compound. It's got to be a whole number. So the reason we did this work is to get to whole numbers. If we look here, this isn't a whole number. So we need to get it to a whole number. And it says on your sheet, under number 4, if you need to get these to whole numbers, and it gives you a couple hints, if the tens place number is a 3 or a 6, you multiply by 3. If that tens place number was a 5, you'd multiply by 2. And that's about as complicated as we'll get. So what we have to do is multiply this whole thing by 3. And if we multiply it by 3, we can get it to whole numbers. And when we do that, we end up getting carbon at 3.000. We end up getting hydrogen at 4.020, and we end up getting oxygen at 3.000. This tens place is a 0, so we can round that off. So if essentially we have carbon 3, hydrogen 4, oxygen 3. That is our empirical formula. We're going to go to the periodic table. We can do all the math with it on our calculator on a piece of scratch paper. It doesn't matter to us, but you need the mass of that. So the mass of 3 carbons, 4 hydrogens, and 3 oxygens. When I do that, I get a mass of 88.03 grams per mole. So I have my empirical formula. I have molar mass of my empirical formula. But it still wants to know the molecular formula. And it says the molar mass of the molecular formula is 88.03. So if you're following the steps, you would take this number and you would divide it by 88.03. You get 1 as an answer. And you're going to realize in this problem that the molecular formula and the empirical formula are the exact same thing. So the difference in these 2 problems, the one that was all typed out for you and the one that I just solved, is this step right here. If these numbers end up all being nice whole numbers, we're good to go. If they're not, we're going to multiply some number through it, and that is step 4. So your homework is to do the next 2 pages. So that would be 55.0 and 55.1. This is a prettier look at what we just did. If you need to, pause the video, take a look at it, and come in for help if you do, in fact, need some assistance. Have a good day, folks.